Last time we talked about what did we talk about? So we did we kind of did a recap of all our deterministic optimal control stuff, right? And in particular, we did like a sort of LQR versus MPC. And then like a DDP versus Durkal kind of comparison, right? And I would see like the stuff we've done so far is basically like the bread and butter of kind of like practical optimal control stuff that you'll see in like robotics and aerospace applications, and like the stuff that's probably most useful that you're likely to see all the time. In particular, like LQR and MPC are, you know, kind of very standard, and the nonlinear trajectory optimization stuff is also super common stuff. And basically putting those two things together will solve, I don't know, probably 90% of like robotic motion planning and control problems. Like it's super useful stuff. So we're kind of now veering, and then also, but the last time we started talking about sort of like Quaternion sort of stuff, we kind of did the Quaternion intro, let's call it. And so now we're going to get into like kind of some extensions of the most kind of stock classic algorithms that we talked about already, and then kind of start veering into, I guess, more interesting sort of extensions and kind of side topics that are occasionally useful and interesting. This being one of them, like how do you extend these things to deal with attitude, large rotations, SO3, Quaternions kind of things. And we're going to kind of do a bunch of those offshoots for the rest of the semester, and then kind of like talk about a bunch of case studies and stuff like that. If you guys have any particular topics that you want to hear about, by the way, in terms of like case studies of like state-of-the-art robot things that you've seen, you want to dig into, or I don't know, just topics in general you want to hear about, definitely send me a message on Piazza or whatever. We can talk about, you know, you can check out what's already in the syllabus, but if there's anything you don't see there you want to hear about, send me a message. All right. So today we're going to basically go in depth into sort of optimization with Quaternions, and basically how to start doing, you know, aerobatic backflip kind of crazy things that involve large rotations using all the tools we've talked about so far. So this is basically the like how to do backflips with robots topic, which is super fun. So first off, just as a quick recap of kind of the stuff we've already talked about with Quaternions. So I'm going to basically do the 5-minute version of last time's lecture just to kind of make sure that stuff sticks and refresh some memories. So first off, right, we think about these things as 4D unit vectors. And they have a multiplication rule that we talked about last time. Sorry, Zoom guys, I have my volume turned on. Are you guys trying to say something? I see the chat popping up.
Yeah, I had a quick question.
Yeah, sure.
So last time you mentioned that there's sort of this formula for Quaternion velocity. Is there a nice way to express like acceleration in Quaternions, or do we not need to do that when we're doing this type of problem?
Yeah, you don't need to do that. Basically, for acceleration stuff, so generally for velocity and acceleration, you're going to use like standard angular velocity vector, and then, you know, that's derivative for angular acceleration. The Quaternion stuff you really just want for representing the pose or configuration. And then what we're going to do here is what we call like Quaternion kinematics, which is the mapping from standard angular velocity, omega, the kind of thing you measure with a gyro, how you map that into a Q dot, like Quaternion derivative, to do the kinematics. But yeah, generally you don't want to write your dynamics down like your accelerations down in terms of Quaternions. It's sort of unnecessary, right? It's got like an extra variable in there that is constrained in weird ways, and it's sort of not convenient. Does that make sense?
Yeah, that makes sense.
Cool. Yeah, we're going to talk a little bit more about this today, and hopefully it starts to click. Okay, so we got multiplication rule for these guys, which we're going to use a star to write down. And it looks like this. We got sort of scalar vector part, scalar vector part. And when we multiply these, the answer is the following thing. And you can see how this kind of looks a lot like a cross product, but like generalized to 4D in some ways. And kind of the right way to think about this is just think of quaternions as rotation matrices, and think of this quaternion product as equivalent to the matrix multiplication of rotation matrices product. Yeah.
Does this multiplication like guarantee all the properties of like a multiplication operator or a vector space?
Yep. Well, so, okay, so this is not a vector space. I think that's one quick thing to talk about. When you say multiplication operation on a vector space, what do you mean?
Or I guess.
Because there really isn't a canonical multiplication of vectors, right?
Yeah.
So what this actually,
like the properties like commutativity, distributivity.
yeah, so it
It's
doesn't
not
commute.
commuted, right?
It definitely doesn't commute, right? So the way to think about this is like matrix multiplication.
Okay.
If you want to get into it, this is an example of a Lie group. So it
Okay.
has all the properties of a Lie group. It has an identity element, an inverse, a product that's closed. It's closed under this multiplication
Yeah.
operation, just like the group of rotation matrices, right? So just think about it in your head as matrix multiplication, and it looks like this. And in all the kind of like standard algebraic ways, it acts exactly like multiplying a matrices, right? You've got your inverse, you've got your identity element, like all the stuff you're used to from. So just think about them like matrices, and it's totally equivalent to matrix stuff. Like we can map this into those left and right multiplication matrices we talked about. You can actually rewrite all this stuff in terms of matrices, and it acts like, yeah, matrix stuff. Right, so then we defined this stuff, right? Such we had the L thing that looks like this. Such that this multiplication is equal to L of Q1 times Q2. So you can turn this into like matrix vector multiplication. We could define the other one, right? The right multiplication matrix like we did last time, although we don't need it today. And then we've got all these kind of other operations that kind of finish us off. So we've got Quaternion conjugate, which acts like the matrix transpose and gives us like the opposite rotation. So it's called Q dagger, and you keep the scalar part the same and you negate the vector part. And we can write this as a matrix operation as well, where T is a 1 and then a minus identity. We have a quaternion identity that is just, I guess we'll write it like Q sub I or something, which is just a 1 and then a 0 vector part. And then we have this other thing that we are going to call the hat map for quaternions, because it does the same thing as the sort of cross product matrix thing, the skew symmetric matrix that we talked about before, algebraically. I don't know of another good name for this, so that's what we're going to go with. And so we're going to can write it like this, right, where it's a 0 scalar part and then just pure vector. And we're going to use this H matrix to represent that, where the H is a 0 row and then an identity block. So it promotes the 3D vector into a 4D quaternion vector with 0 scalar part. Okay. Any questions about this stuff? This is all the stuff we did last time, right? It's kind of like algebraic things and like how to write them as matrices, how to multiply them, how to invert them. Yeah, everybody good with this stuff? Okay, so now we're going to talk a little bit more about like geometry and kinematics and stuff like that, and how to like differentiate these things. Kind of basically a recap of last time, but like with more geometry flavor and kind of explaining these things in a different way that may make more sense to some of you, may not. I'm not sure. We'll have to see how it goes. Okay. So yeah, this goes pretty deep and it's kind of, I think it's interesting personally. I don't know. So the sort of first thing to say here is that quaternions, they're 4D unit vectors, right? So just thinking about that, right? Like what is the set of all, like in 3D, if I took all 3D unit vectors, that defines what shape? A sphere, right? So it's a hollow sphere, right, in 3D. So just the same way, the set of all 4D unit quaternions defines what's called a 3-sphere in R4. So it's called a 3-sphere because the surface of the sphere is 3-dimensional, right? Just like the surface of a sphere in 2D is 2-dimensional. So like the tangent plane to that sphere is 3D. That's the way to think about it, right? Just like the tangent plane to like a globe is a 2D plane. Okay, so cartoony drawings, we're going to draw this like quaternion unit sphere thing. So here's like a particular Q, say. So Q lives on a sphere. In R4. Now, next question, based on that, just from like basic geometry kind of considerations, where does Q dot live? So if I have this Q, this might, living on this sphere and it's moving around, it's tracing out some curve on the sphere. At any instant in time, if I like pause, I look at that Q of t and I take its time derivative, Q dot, where does Q dot live geometrically speaking? On what surface? Nope. That's right. Yeah. So that's the right answer. It doesn't live on the sphere. It lives. So if I'm moving around on the surface of the sphere, instantaneously, if I take that derivative, it's like tangent to the sphere at that point where the Q is, right? It's not on the sphere. It's on that tangent plane to the sphere at that point, right? Okay. Does everyone get that? It's the standard kind of like, tangent derivative idea, just sort of like in this. So if I sort of like draw then at this point, the Q dot will look something like this, and it lives in this 3D tangent plane or hyperplane or whatever you want to call it. Okay, so the kind of key insight to like keep in mind here is Q is 4-dimensional, a 4-dimensional vector, right? We talked about, but has this unit norm constraint. Q dots, though, at a given point, they live in this 3D tangent plane, right? So in some kind of like deeper sense, the derivatives are 3D, right? And that corresponds to the fact that you have 3 degrees of freedom, right? And like the derivatives are related to like your angular velocity that, these are all 3D quantities. So like the important like key geometric fact here is that the Q dots are really 3-dimensional things, and they should be 3D things and not really 4D things. And this is kind of why we talked about how you want to write your sort of pose as this quaternion thing that's 4D with this constraint because it doesn't have singularities, but then the rest of your dynamics, when you start taking derivatives and you write down angular velocities and then accelerations and all that stuff all lives in this tangent space and is all kind of should be 3D. Does that make sense? So we're going to basically, the whole game here is we want to keep the pose stuff 4D, but then all the dynamic stuff that are higher derivatives should all be 3D, like we're used to basically. Okay, so here's sort of some more on this. So we have this Q dot thing that's sort of in R4. And we have omega, the angular velocity vector, the thing coming out of your gyro, right? And that thing is in R3. And we have this kinematics thing that we derived last time for Q dot in terms of omega that looks like this. Q times this like omega hat thing, which is equal to 1/2 our L matrix times our H matrix times the omega. Okay, so like the question here is, knowing this like omega is 3D thing, this Q dot tangent plane thing, geometrically, where does omega fit into this picture? That's the question. So like there's some kind of version of this like tangent plane idea going on here, right? And the Q dot, as I've written it here, is a 4D thing. And then this omega is a 3D thing, sort of, right? There's only 3 numbers. If I look at this kinematics thing for a second, kind of like stare at it a bit and think about this whole idea of like these things being like matrix multiplication. And if you think about back to when we did this kinematics thing for the rotation matrix, we had like Q dot equals Q times this omega hat thing, right? Thinking about that and like what that does when I multiply by the quaternion, it's probably not obvious here, so I'm just going to write it down. We can talk about it, but think about like geometrically what's going on here is basically we have, say, Q over here. We have Q dot is like, you know, kind of rooted at Q in this particular tangent plane here, say. So Q dot's in this tangent plane. Turns out what omega is here is basically it's the derivative written in one particular tangent plane. It's written in the tangent plane at the identity. And then what this kinematics is doing is taking that tangent plane at the identity, think about it like the North Pole, if you like, and it's rotating it down to where the current Q is. So that's kind of the idea. Let's see. So let me write this. We'll do it like this. So here's omega, and it's living in this North Pole tangent plane. And then Q, the Q in this, so this equation here, what this is really doing is taking omega from that North Pole tangent plane, and it's multiplying it by Q to rotate it down to where your current Q is. And that's going to give you like the actual Q dot in the correct tangent plane based like centered it at the current Q. Does that make sense, everybody? So that's, and the kind of the way to think about this is when we have a gyro, right? That's this omega. The gyro is bolted to your body frame. So you're kind of always measuring it in the body frame. And this Q is kind of like rotating you from body to inertial and sort of somewhere else, right? Not at that identity element. So if your body frame is instantaneously lined up with your inertial frame, then your Q in this kinematics is the identity, right? And then it really basically, Q dot really basically is that omega. Does that make sense? Okay, so that's a bunch of kind of weirdo geometry. I don't know if that's insightful or helps at all, but that's kind of what's going on. Any questions while I write this down? Okay. So all good so far? So to sort of maybe give you a little more intuition for what's going on here and maybe make the ECE types here feel a little more at home, we're going to now talk about this in analogy with complex numbers in 2D, aka complex phasors, which hopefully everybody's heard of and seen before. So the Quaternion stuff we're just talking about is all basically the 3D sort of generalization of complex numbers. And all the same kind of stuff applies there. And maybe that makes more sense. So we'll do that real quick. Okay, so here what's going on. Let's say I have, you know, my complex is sort of XY unit vectors. And let's say I have a particular unit vector up here, we'll call V. And then I can write down its sort of X and Y components. And I have this angle theta. Let's say we measure it from here. And if I write this down, or let's call this, yeah, so we've got V equals, say, cos theta plus I sine theta, if you're doing kind of the standard complex stuff, right? And this is kind of your X component or real component, right? And this is your Y component or imaginary component. And if we stack this up and write it as a 2D unit vector, we would get, just this. This is going to be, sort of cos theta, sine theta for the x and y components. Notice the closeness to this versus the Quaternion kinematics that we wrote down, right? With the scalar vector part stuff, it looks almost the same, but there's this weird factor of 2 thing. Okay, so if I just take this, and also the other note here is sort of just like the Quaternion, right? You get V transpose V equals 1. It's unit norm. Okay, so if I take V dot here, the time derivative, I can write this as partial V partial theta times theta dot. If I just chain rule through that definition, if I do that, I'm going to get the following thing, right? So I'm going to get minus sine theta for the derivative of the cos, and then cos theta for the derivative of the sine, times theta dot. And I can write this down, if I kind of stare at this for a second, this is equivalent to me writing the following thing, like a rotation matrix, cos theta minus sine theta, sine theta, cos theta, so it's like 2D rotation matrix, times 0 theta dot. So like the theta dot written as like pure y component, sort of like tangent vector at a particular, centered at theta equals 0 at the identity, right? Which here is like on the x-axis over here. So the picture of what this is doing, this is a rotation matrix, 2D rotation matrix, right? And then this thing where I've got 0 scalar part and just y component, or 0 real part, pure imaginary. This is like the 2D version of our Quaternion hat map thing, right? It's promoting the scalar into a 2D vector with 0 real part, or pure imaginary or whatever. This is sort of 2D hat map. And if I draw the picture of what's going on here, it's taking, so that vector that's got, so let's say here's my V. This 0 theta dot thing, that's drawing the tangent, and so this whole thing is a unit. This is like the unit circle in the complex plane kind of deal. And I'm writing the derivative here. It's got 0 y component, and then just a y component. So it's actually over here. So this is like my theta dot. And then this rotation matrix is rotating me over here to this tangent plane to compute the V dot. Does that make sense to everybody? So this is like what those Quaternion kinematics or rotation matrix kinematics are doing. They're just kind of like up a dimension, like the 3D version of this complex story. And so here, right, like with these complex phasors, we're using a 2D unit vector, right, a complex phasor, complex number thing, to represent a planar rotation instead of just a single angle. Actually, this also gets at a bunch of the reasons why Euler angles are worse than kind of Quaternions in a bunch of ways, right? So here, one of the things you'll run into, right, with using just an angle for planar rotation is that it has wraparound issues. And if you've ever tried to finite diff these things, there's like ambiguities because it's like actually modulo 2 pi and all this kind of stuff. And all that goes away if you write it using the 2D phasor, unit phasor thing instead of the angle. So there's a lot of similarities. Okay. Write some stuff down. Cool. Everybody get that? Any questions about any of this stuff so far? Okay, so that's sort of velocities and kinematics of like rotations. And this is what it looks like in 2D, and then 3D, you got the stuff we already did. So now we're going to start talking about differentiating Quaternions. And so the reason we just did all that discussion, right, is like, hopefully now it's clear, like this idea that derivatives of these things live in this tangent plane, right? And even though the quaternion itself is like 4D, just like angular velocity, right, is the time derivative of a quaternion, we really don't want to use the q dots. We want to do the omegas, right, which are 3D most of the time. So when we start differentiating like more general functions with respect to quaternions, the derivatives always live in this tangent plane. And we actually want the derivatives to be 3D, not 4D. That's sort of the whole reason for all of this baggage. That's the key idea, is that the derivatives live in a different space than the q's themselves. Okay, so key ideas. Number one, derivatives are really 3D like tangent vectors rather than 4D quaternions themselves, right? And then two is that rotations compose through multiplication, a la quaternion multiplication or matrix multiplication, not by addition. So like this goes along with the fact like that they're not vectors. They're not a vector space. They don't act like vectors. They don't commute, right? Like vectors, if I add two vectors, v1 plus v2, I can also do v2 plus v1. Order doesn't matter. If I multiply two rotation matrices, the order definitely matters, right? So that all this stuff is kind of why this is weird and a little different. So these are the two things you have to keep track of. Okay, so if you keep these two things in your head and you kind of like turn the crank on the math, this stuff will all work out. So here's sort of the first step is we're going to talk about infinitesimal rotations, or sort of like differential delta rotations. Yeah.
Can you please explain the second point?
Yeah, so like, okay, so if I have, say I want to do, if I compose two rotations, so like, let's say I have a 90-degree roll and then a 90-degree pitch. If I do 90-degree roll, 90-degree pitch, I end up here. If I change the order and I do 90-degree pitch, then 90-degree roll, I end up here. Completely different answer, right?
Yeah.
So that corresponds to multiplying the two rotation matrices in a different order. So that's saying they do not commute with each other. You can't flip the order and get the same answer. Whereas if this were translations, like if I have v1 plus v2, if I do v2 plus v1, I get the same answer. I end up in the same spot. So translations add like vectors, rotations multiply like matrices. So this is a very different thing, and it takes people a while to like wrap their head around this. It's weird, but like it's really not like, this is 3D spatial stuff you can think through in your head really easily. It's like, don't get too hung up on the math. Like whenever that gets like, try to think about pictures. Like, so, I like the roll pitch versus pitch roll, thing. Totally different, right? So this is, and that's just the fact that the matrices, or the quaternions, the order matters, right? So you have to think about this when you do this stuff. You can't just flip orders. And you have this kind of like 3D, 4D weirdness happening, where the derivatives are sort of these 3D tangent things. Even when the pose representation is like a 3x3 matrix or a 4D unit quaternion, the derivatives are still 3D, like omega, right? In the kinematics. Okay, so very similar to the kinematics. We're going to talk about this like idea of infinitesimal rotation. So I'm going to write this down like an infinitesimal tiny, just think about a tiny delta quaternion, delta Q, small rotation. If I write that down like a little delta Q for some small angle, think about small angle approximation kind of ideas, right? So if I write that down, I'm going to get like cos theta over 2 and then axis of rotation times sine theta over 2, like we talked about last time. So when we say small rotation, remember the axis is still a unit vector, still 3D unit vector. We're talking about small theta. So if I make a small theta, small angle approximation of this thing, what do I get? Help me out. I'm going to get a 1 up top because cos linearizes to 1. I'm going to get just 1/2 a theta down bottom, right? And then this thing, remember what we said the a theta thing is last time? That's an axis angle vector, right? If I multiply them together, and we call that phi. So that's just the axis times the angle. And so this is, so if we kind of like, this is, you know, where phi here has small norm, right? The norm is theta. And then I can write this thing down. If I kind of expand that out, right? This also is equal to an identity quaternion, where it's 1, 0 on the bottom, plus this thing, right? Which is equal to identity quaternion plus our like promotion matrix hat thing times phi. Okay. So that's what's going on when I like linearize a rotation. I can then kind of think about this as if I wanted to like Taylor expand or perturb a quaternion, like if I, you know, like if I compute a Taylor expansion and I get like an x plus delta x going into a function, remember when I compose the quaternions, I'm not going to do q plus delta q. What I'm going to do is q times delta q, because they multiply, they don't add, remember? Okay, and the order matters and all that stuff. So we've got to do that now instead. So when I compute like a q prime equals q times delta q, which is the equivalent of like, you know, x prime equals x plus a delta x, but I'm going to multiply now. This is equal to L of q, left multiply, times, I'm just going to plug in the stuff from before, identity plus 1/2 h phi, right? And this is equal to so if I like, you know, kind of like do this out now, it's q, this is equivalent to doing q plus 1/2 L of q h phi. So kind of the end of this exercise is that we're going to end up getting, instead of like q plus delta q, you end up basically, if you actually follow this through and Taylor expand and everything, you're going to get q plus this weird extra Jacobian times phi. That's basically the result. So like, if you want to do normal differentiation kind of stuff and like have little deltas hanging around, you want to multiply, not add. And if you multiply and then do the Taylor expansion, you'll get like basically the original q plus this delta term that has this extra Jacobian. So the whole idea is basically at the end of this, you're going to pick up this extra Jacobian, and we're going to call this thing in here, we're going to call it g of q. It's 4×3 matrix, right? Because it's mapping the 3D little phi into a 4D delta q. And we're going to call this the attitude Jacobian. And so what we're going to now do is basically all you need to know is whenever you see a quaternion that you want to like diff in a function, essentially you're going to take the derivative as normal and then slap on this attitude Jacobian, and things will generally work out the way you expect. Let's see, some notes. So one more note here before we get into that is that we used a particular choice for the representation of phi. Like we used this axis angle representation so far. It turns out you can use any 3-parameter small delta rotation representation you want, and the math basically works out the same. So this could be axis angle, it could be the vector part of a quaternion, it could be these things called Gibbs parameters, it could be even Euler angles if you're a sadist. And basically this Jacobian is the same no matter which choice you make, which is kind of slick. Except for possibly a factor of 2, depending on, you know, like there's a factor of 1/2 floating around in there. So depending on which choice you make, like I think if you choose Euler angles, it's it's not a 1/2 anymore. So like some of the choices might have a different constant out front, but generally speaking, it looks the same. Okay, so some examples of these, just as an aside, which you may have seen before. So far we did axis angles, which look like this. So we do like sort of norm. This is the theta, right? This norm of that guy. And then down here, we just have something like phi over norm phi to get the axis, and then the theta over 2. So this is what we have right now, right? So for our axis angle. You can also do a bunch of other things. So this. You could also do, for example, just use the vector part of the quaternion as your phi. So that would be, that, and then what would the upstairs look like to make it normalized to 1? So it's going to look like this. I want the whole norm to be 1, right? So to make that work, I just do this guy up here for the scalar part. And now it normalizes to 1, right? Okay, another choice. So this is just vector part of the quaternion. Maybe I should put, yeah, and basically if you actually kind of look at this, you'll see like basically if I linearize all of these, they end up being the same, right? For small phi. That's kind of the point. Another one I can do is what we called Gibbs vector or Rodriguez parameters. Has anyone heard of this before? Yes. Okay. Some people have. This is more of an aerospace thing, but looks like this. Okay, so these are like a bunch of options. Like I said, you can also use Euler angles. Don't recommend it. And then we're going to, for the purposes of this class, we're going to just use the vector part of the quaternion. That's kind of the easiest, most straightforward option. So that's what's going to be on all the homeworks, but you can plug in any of these that you feel like. Okay, so now on to, so this basically, this whole machinery is to let us differentiate quaternion functions by just kind of slapping that attitude Jacobian on in the right places. And here's some examples. Okay, so if I have some f of q that is a scalar function, a scalar valued function of a quaternion, i.e. like a cost function, right? So this thing eats a quaternion and spits out a scalar. So this, by the way, the Blackboard bold H is for Hamilton. This is the notation for quaternions after Hamilton. So this is the gradient of a scalar valued function. So this looks like grad F. What we're going to do is basically, one way to think about this is we're going to just chain rule the composition of like the original F of Q with the definition of like the this like axis angle stuff. So it's going to look something like what you're really doing is basically partial F partial Q times partial Q partial phi. And if I do that, I'm going to get partial F partial Q times the G attitude Jacobian matrix. That's it. So, and then again, we'll go through, I'm going to write these down and then we'll actually do an example of this. It's like a very practical example. So, so that's gradients. Now we're going to talk about Jacobian. So if I have like an F of Q that maps from Quaternion to Quaternion, when would this happen in like our kind of stuff? So the first one's like the gradient of a cost function, right? That depends on your attitude. How about here? When would I have a function that eats a quaternion and spits out another quaternion in like control? Anybody? Yeah? Well, like specifically in the pieces of our optimal control problems that we've been solving, right? Like the first one would be like your cost function. This is your dynamics, right? It's like QK, like QK plus 1 equals F of QK stuff, right? It's like eat a state, spit out a state, right? So if you got a quaternion in your state, this is what you're dealing with, right? So Jacobian of a quaternion valued function. So here, yeah, think about dynamics. And the idea here is you want to basically do this attitude Jacobian trick on both the input and the output, right? Basically, you have to do it on both ends because it's got to do it on the input side and it's spitting out a quaternion, so I got to do it on the output. So what this is going to look like is like basically phi prime on the output side is going to be like you're going to basically smush the kind of original Jacobian of F, just treating it like basically what you do in all of these examples is you take the Jacobian, you take the derivative just treating Q like a normal vector, and then you smush it with these Jacobians. So here you're going to get a transpose, and then here you're going to get kind of just a regular thiel. So this whole thing times phi, and we're going to call this thing in the box the Jacobian, and this is going to be what dimension? 3 by 3, that's right. So because you want to basically eat and spit out these tangent plane vectors, right? That's the idea. And kind of the weird quirk here, right, is remember we talked about G is basically rotating the tangent plane to the right spot. So another way to think about this, if this thing's eating one quaternion and spitting out another one, these tangent vectors are actually living in different tangent planes, right? One's living at, like if this is a dynamics function, on the input side, it's the tangent plane at QK. And on the output side, it's the tangent plane at QK plus 1, some other spot. So that's why you see on the right-hand side, it's G of Q, like the input one. On the right-hand side, it's G of F of Q, like it's the output side, right? So it's the G evaluated at the output, the original output of the function. And yeah, I guess we write like Q prime is assuming we have this kind of setup. And yeah. Okay, any questions about this? Yeah.
John, I'm not sense, but I thought we said that the Q prime is going to be Q plus GQ. But when we look at dFdq times dq d5, we just say it's GQ.
So basically, yeah, like this, what's kind of going on here is this part, this like, so maybe this will make more, let me write this thing down. So when I think about this, like one way to think about it is, remember we want to have like multiplicative kind of stuff going on rather than additive. So the right way to think about this is like one way to, so let's say I start out with a function that's q prime equals f of q. What I want to do is like the following thing. I want to have like the delta is, so this is like q prime times delta q prime equals f of q times delta q. This is like what I want to get, right? And I want to solve for like the delta q prime as a function of the delta q, like small change on the input. What's the small change on the output? Just like normally we do with derivatives. So then if I do that, what I'm kind of doing, right, is q prime, I want to assume small delta q and do my like axis angle trick. So that looks like q prime times this axis angle thing. So like this, where this is like the phi prime, right? And then same thing on this side. And so what I'm really doing here is I'm doing this, and then I'm asking what is partial phi prime partial phi. That's what I'm really doing, right? So I'm like putting on a multiplicative perturbation on both sides. And I want to ask like, what's the first order Taylor expansion-y thing that's going to give me the 3D perturbation on the output as a function of the 3D perturbation on the input, right? So I'm basically asking, you know, to first order, what is that phi prime going to be as a function of phi? That's what this is telling you. Does that start to make sense?
Yes.
Yeah. So it's like multiplicative delta on both ends, and then ask what's that Jacobian thing. Yeah. It's weird because they have to be multiplied rather than added, and because one's 4D and one's 3D. Okay. Everybody with me still? Hope so. Okay. So yeah, this is like basically this thing. And it's just doing the chain rule through that whole thing, right? Okay. So last one we got to do. So we've done gradient of a scalar valued function, Jacobian of a Quaternion valued function. That's pretty much, that gives us, you know, a lot of, the last one we need for doing like the Newton method stuff is the Hessian of the scalar of the cost function, right? So that's the last one. So here we go. So here's, we're going to write this as del squared f of q. And the first term, this is again like the Gauss-Newton versus full Newton story kind of thing. So the first term is going to look like this. Which looks exactly like the Jacobian thing, right? But with the d squared f dq squared inside. And then we're going to get a second term that looks like this. So this is a 3x3 identity. And this is a scalar. And this whole thing comes from the like derivative of G itself. Okay, so, and similar to our other story, basically the first term is like the Gauss-Newton term, and the second term is like this, the full Newton term. So if we're doing Gauss-Newton, you can throw out the second term, basically, which we're going to see in a second. Okay, so that is all you need to do anything optimization that you want to do with Quaternions. That gradients, Jacobians, and Hessians. Cool. That's these are all the kind of the recipes you need. And basically now we can do gradient-based, you know, Newton style optimization. Yep.
So like df/q, when you do that, are you basically like treating q as if it is like a
Yes, exactly right. Yeah. So wherever in this stuff, wherever I've written like partial f, partial q and any of this stuff, it's just vanilla, like treat it as if it's a vector. Yeah, so I think like this is kind of getting at the heart of what you want here. This stuff, which I kind of sloppily wrote out. This is basically like telling you this is algebraically, if you want to mechanically think through this is what's happening. Basically, I'm saying I want to multiply by some delta rotation on the input to the function. And then I want to, figure out what the resulting like multiplicative perturbation would be on the output. And so if I like write it out like this, and then literally just evaluate that with the chain rule, like partial phi prime, partial phi, that's what this is, right? And it turns out it has this nice flavor where you just basically treat it like the standard derivative and just slap on these attitude Jacobians on input side or output side as needed, wherever there's a quaternion. Okay. So now we can do Newton's method. And sort of TDP and SQP, all the stuff we've been doing with quaternions. You can do super fun things. Okay, so let's do an example. So the example we're going to do is something called Waabs Problem. Has anyone heard of this before? Anyone not in my lab? Yeah, probably not. Okay, so this is a very classic estimation problem. It's a problem of doing pose estimation, doing attitude like estimation from a set of like, given a set of like feature vectors that you know in the environment, and then given observations of them in the body frame, like from a camera. It's basically if I have a bunch of features in the environment, and then I have like measurements of them, like camera measurements, where I measure them in the body frame. And I want to figure out what the rotation is between the inertial frame and the body frame. So that's the problem. So given a bunch of vectors to known features in the environment, determine the robot's attitude. This problem has a fun sort of side note history. This was posed as a challenge in a journal in like the early 60s. This is a very like space age. So where this originally comes from is on spacecraft doing attitude determination from star trackers. So you have a camera, you have a map of the star field, and you like see the stars in the camera, and you want to match the stars up to your map and figure out what the satellite's orientation is in the inertial frame. And it was originally posed as a challenge to the community in a journal by someone named Grace Waabs, who's a professor at Wisconsin in statistics for a lot of years. And like this problem's named after her. And I think she did it like, I think she was like a grad student, maybe even when she originally did this back in the early 60s. And like, it's like a total afterthought into her career. And like, it's got her name on it. It's famous in like aerospace engineering. It turns out this problem has a closed form solution, which is kind of fun, but we're going to do the Newton method version. Okay, so here's what we're going to do. We're going to take the min over q. So it's basically least squares. So we have min over q of some loss function, j of q, that looks like this. And this we're going to just write as r of q. the residual. Okay, so these are sort of known vectors or known features in the inertial frame, in the N frame. So like, e.g. from a map. And then these are the measured vectors in the body frame. And when I say these are all unit vectors, by the way, right? They're directions to features. E.g. from a camera. And then, yeah, this thing is the residual, right? From like kind of your classic like least squares kind of stuff. Okay, any questions about the setup? So if that's the rotation matrix from the body frame to the inertial frame, right? That's how we've defined all this stuff. So, and we want to optimize the Quaternion, the unit Quaternion here. That's what we're so we're going to plug in there. We talked about how to convert a Quaternion to a rotation matrix. That's all we're doing. You could also write it down as just like the Quaternion matrix sort of multiplication sandwich version of this, but yeah, that's it. So like what we're doing is we're saying we're measuring all these XBs with a camera, got all these feature vectors, and then we know what they are from a map, say, like where they are in the inertial frame, that's the XNs. And I want to figure out the rotation matrix Q or Quaternion little q that maps these things into each other, right? That tells me what my pose is in and that it's an attitude, so it's always by convention the rotation from the body frame to the world frame, like we said, right? Does this make sense to everybody? This loss function that we're going to minimize. Okay, so we're going to now write down what this residual function looks like. Then is going to be R of Q equals. We're going to stack up all of these x's. Down to like xm. Used m there because I used n for the frame. Right, so this is the residual vector. So it's just stacking up all of the errors, right? So this has size 3m by 1, because each one of those, there's m of them, and each one's a 3D vector, right? And if I kind of like do my chain rule thing, what I'm going to get is, what I want is like the Jacobian of this thing as a function of q. And this is going to be, we're going to just do the chain rule, and we're going to get partial r, partial q, the standard treating it like a 4D vector times the attitude Jacobian. And if we kind of like eyeball the dimensions, this kind of all makes sense. So this will be, this thing is going to be 3m by 3 is what we want. And this thing is going to be 3m by 4, treating q as a 4D vector. And then this thing is going to be 4 by 3. And so when I sandwich that all together, the dimensions work out. Okay, everyone good so far? So that's the residual. And remember, I'm minimizing the sum of the squares of the residual. That's like least squares, right? So we're going to do this with the Gauss-Newton method that we've talked about a whole bunch. So let's write that down. Okay, So we're gonna do the following stuff. So we're gonna take this Jacobian. We're gonna make a guess for Q first. Then we're gonna evaluate, actually, maybe we should do, yeah, actually, before I do this, how many people have done least squares before with Gauss-Newton? Only a couple people. Okay, so let me do the background Gauss-Newton least squares thing first then, before we get into this. So apologies. Let's do that first. So this is actually where Gauss-Newton originally came from, by the way. Least squares problems. Okay, so classic least squares problem would be like min over x of some loss function j, which is always the least squares thing is always, it means you're minimizing the sum of the squares of the residual, aka 2 norms squared of the residuals. The residuals are like whatever your errors are, right? And this is equal to 1/2 r transpose r. So that's where least squares comes from. The thing you're minimizing is the sum of the squares of the residuals. So if I write down the derivatives of this thing, I'm going to get, say, partial j, partial x, the gradient. If I kind of just diff through the definition, right, of this least squares objective, it's going to be r of x transpose partial r, partial x, right? If I take the Hessian now, I'm going to get d squared j dx squared is going to be, so if I differentiate that line above, I get the product rule thing. So the first term is going to be, if I just differentiate the r on the left, I'm going to get partial r, partial x transpose partial r, partial x. And then if now I have to also diff the second term, right? So I have to get like this d squared r thing. And for this, I can use the matrix calculus trick. So this looks like I cron r transpose d squared, like this. This is our vec trick stuff that we talked about. Okay, so unsurprisingly, we've already talked about like Gauss-Newton versus full Newton a whole bunch. So that's what the Hessian is. And then what's the Gauss-Newton approximation, as we talked about before, like with DDP and stuff like that. I'm just going to throw out the tensor term and keep the one on the left. Yeah. And this is the original Gauss-Newton, actually. This is where it comes from. Okay, so I'm going to get then like my my Newton step, Gauss-Newton step is going to look like, then we're basically just, so the Newton step would be this. And we're going to approximate it as just the first term. So it's going to look like partial r, partial x, transpose partial r, partial x. That's our approximate Gauss-Newton Hessian, right? Because we threw out the other term, inverse times grad j, which we already wrote down above, which is going to be partial r, partial x, transpose r of x. So that's the Gauss-Newton step. Does anyone recognize that equation? Does that look familiar to anybody? Anyone who's done least squares? Yeah. Yeah, that's the pseudo inverse of the like residual Jacobian, right? Cool. So that's where the pseudo inverse comes from, blah, blah, blah. There's all connected. So it's basically doing linear least squares, right? That's what you get when you do a linear least squares problem. Here, you're just going to iterate it. So like Gauss-Newton equals doing like the pseudo inverse linear least squares thing and just iteratively on the nonlinear problem using the Jacobian. So you convert your nonlinear least squares problem into a linear least squares problem, solve the linear one, get an update step, repeat, repeat. Cool. Okay. So now that we're good on that, everyone good on that? Yeah.
Sorry, I'm trying to work through the dimensions on these. so R of X is like an n by one.
R of X is this, yeah, this residual vector that is, yeah, basically whatever your loss function is, like it's the sums of squares of some errors, right? So the residual is just all the errors stacked up in a big vector. Yeah.
Okay, so it's n by one, and then dj dx would be n by n.
Nope. So you've got two different vectors floating around. So you have this residual vector, which is say size m, and then you've got, it's a function of some parameters x, which are a different size in general, right? So that could be, you know, so let's use different letters because you're not gonna be able to hear me. So like, let's say that R is dimension P and X is dimension Q. So, okay. So now partial J partial X is gonna be a row vector of dimension Q. It's the X dimension wide, right? And then the Jacobian is gonna be like P by Q. And then we wanna, when we do this squarey thing in there, where I take the transpose and multiply together, that's gonna give me a square matrix now that's size Q by Q. So I can invert it and like solve for the X's, right? Does that all make sense? Everyone good with that? Anybody else have any questions about this? Cool, yeah. Okay, so now that we know like kind of the standard Gauss-Newton thing, which is literally just doing linearly squares using a linearization, we're gonna do it with the Quaternion. And I always forget how to spell this. Okay, so we're gonna first like have some guess for Q. And then we're gonna do, first we're gonna like evaluate our residual Jacobian thing using like the recipe we had before. Then we're going to compute our Gauss-Newton update. And we're going to use all the standard stuff to do that. So we're going to compute this phi, remember, this like multiplicative 3D thing. And that's going to be this guy. And then I'm going to update my Quaternion by doing the multiplicative update thing. So I'm going to convert the phi back into a full Quaternion and multiply it on to my previous Quaternion. So this is like, and in general, you would have a line search in here. It turns out for this problem, it's a very benign, nice problem, and you don't need a line search, but in general, right, like all the usual regularization line search stuff would apply here. So do the stuff until you hit your convergence criteria. So in this case, right, phi is the correction thing. So norm phi is like the thing we're trying to drive to 0. Okay, any questions about that? Yeah.
So what is F and the first
Oh yeah, my bad. That should be R. Okay. Anything else?
You can just scale phi by alpha, right? And look that fine.
You mean like to do a line search? Yeah. So you would literally do the line search on phi in the normal way, but you would do it in that multiplicative update, right? So just like in normal Newton, we do like, add on the dx, right? Like you do x plus delta x. Here, like as we talked about, multiplicative update, right? And the reason is if I just added, say I computed, if I did naive Newton on this, and I like computed some update Q and added it on in like just super naively Q plus a delta Q, it would not be a unit quaternion anymore, right? You have no way of guaranteeing that that Q plus delta Q thing has unit norm. Whereas if I multiply it on like this, I'm multiplying one unit quaternion by another unit quaternion because I've set that up so that when I plug the phi into that definition, it stays unit norm. So by doing that, I'm guaranteeing that it's a valid unit quaternion. So that's kind of part of why this works out. And turns out, yeah, if you do the naive Newton on this, it works horribly. Like it just straight up doesn't work. So you have to do this. You can hack the naive Newton to kind of work by putting a bunch of normalization hacks in all over the place, but it ruins the convergence rate and it does very poorly. Okay.
Is that why we're sort of like driving this phi to 0 instead of the residual as we would in the previous like normal Newton?
Yeah, I mean, you can also check the residual. That's fine too. They're actually kind of equivalent, right? Like if R goes to 0, like norm R goes to 0, this thing will also go to 0. So maybe I should write it that way actually to be consistent with our other stuff. Let's go with that. That's probably better. Thanks.
Yeah, no problem.
Yeah,
Just a quick question, where is the minus coming from?
that's the standard Newton thing, right? Like if I write, yeah, you like it always has a minus sign in Newton's method, right? Because basically you're doing like Taylor expansion equals 0, and then you like move it over to the other side, right? And whatever, and that you get a minus sign. Okay, everyone good? So we're gonna now like do this, do some code stuff. Here's the code. Okay, so what's in here? So this is the hat cross product matrix thing that we talked about. This is the left multiplication matrix operator thing for like representing the quaternion multiplication. This is the right version, although we don't use it, I don't think, in here. This is that T matrix that does the quaternion conjugate. This is the H matrix that does the promotion hat map thing to make a 3D vector a quaternion with no scalar part. This is the attitude Jacobian, so the 4x3 thing, right? Here's the actual fun part. So we're going to generate a random quaternion, like a random rotation. We're going to do that by generating a random 4 vector and then normalizing it. Turns out this is a perfectly reasonable way to generate random rotations if you care. Actually, yeah, sampling rotations is a fun other conversation. Like if you want to generate random rotations, like how do you do that? Like how do you generate a random rotation matrix? That's a fun conversation to have. Turns out this works fine for quaternions. So we're going to do this to get the random unit quaternion. Then we're going to convert it to a rotation matrix using the recipe we talked about yesterday, or 2 days ago, I guess. So now we have a random rotation matrix. Now we're going to generate some data. So here's a bunch of random vectors, like 10 random vectors in the world frame, say. I'm then going to normalize them to make it sort of, work out with the Waabs setup. And then I'm going to convert them into the body frame by taking our truth rotation, just rotating everything. At this point, I could also, if I wanted to make this more realistic, I can add noise here to the body frame measurements, like as if you were measuring with a camera. We could do that next if you want, actually. Cool. Here's the residual function. This is the so-called Waabs loss function. It's exactly what we just wrote down, right? So I'm taking that, I'm doing the, convert to rotation matrix thing in here, subtracting, cool, and that should be 0, right? Okay, so I'm gonna make a random initial guess, quaternion, unit quaternion again. I have no clue, this is totally random. And here's the Gauss-Newton method. So yeah, probably should write this on the residual next time, but this is easier. So, okay, we compute the residual. We compute the Jacobian of the residual. Here, this is as if it's a 4-dimensional vector, right? I just use 4diff, auto diff it. Now I do my attitude Jacobian trick. So here's my sort of Jacobian with the attitude Jacobian. Here's my Newton step, like we just wrote down, which is pseudo-inverse solution, basically. You shouldn't do that in real life. That's bad. You guys probably know that. You should really use a QR decomposition, but for now, this is fine. And then we have our multiplicative update, like we just wrote down. So let's do it. So 5 iterations, and here's some potentially interesting stuff. Okay, so you can see this is like machine precision for the residual, or this is, me checking it. We're going to do this a couple more times because I want to show you something interesting. So, okay, any questions about that? That like looks about right. Yeah.
Wait, sorry, there's like a big R of Q somewhere up higher. What is that?
Where?
In the residual function,
Uh,
big R Q times.
oh, yeah. So that's me. That's just converting the quaternion into a rotation matrix.
Okay.
It's doing this thing, which I wrote kind of like, I'm slightly, that was maybe a dumb thing to do. So it's this. So here I wrote it with a pair of H's on either side, which just indexes in like to a 3x3 block in that 4x4 matrix. So here I just indexed in and pulled it out instead of using the H's, which is probably dumb of me, but slightly confusing, but Okay, so let's run this a couple other times. We can also try like adding noise and stuff if you want. So random stuff, blah, 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 run it, converges in 7 iterations last time. Okay, that one didn't do it. So let's try a couple more times. There's something I want to happen that might happen in the sec. We do this a couple more times. Nope, still hasn't happened. Okay, so the thing that I'm going to try to get to happen is we choose. Still hasn't happened. Okay, so I wrote this because what will happen eventually if you try this a handful of times, and statistics are not working out for me right now, is that occasionally we'll get this will evaluate to something big, and this one will actually be close to 0. And it hasn't happened yet. Can anyone tell me why? It will happen, I promise. It should be about 50-50 odds on that. And we're really like seeing a serious statistical anomaly here. Okay, so we talked about this whole double cover thing and how in general there's 2 quaternions like Q and minus Q that correspond to the same rotation. And so if you got the minus Q, Q true out as the answer, then this one would be 0 and this one would be something not 0. And again, basically the story is Newton's method, local method, you're going to converge to whichever one is closer to your starting guess. And you can't say a priori which one that'll be. Both will minimize the residual, right? So both are the right answer. But this is a thing that you basically always are going to have to worry about when you do practical control stuff. Like basically, you have to think about this, for example, when you write down your cost function, you have to make your cost function have local minima at both Q and minus Q. You have to be a little smart about this. Otherwise, you can get stupid behaviors. The classic example of stupid behavior is this thing called the unwinding problem. Essentially, if you write down a cost function or something that only has a minimum at Q and not at minus Q, you can get into situations where the system will wrap around 2 pi for no reason. So if you're like epsilon away from minus Q, but your cost function says minus Q is bad and only Q is correct, you'll actually do a 2 pi rotation to get yourself to Q, which is like, again, you're just rotating around 360 for no reason, right? So that's something to worry about at some point, maybe. Otherwise, I think that's about it. And we're right about at time. So questions, comments, I'll hang out, but otherwise you guys are free to go.